Hello everyone. In this video, we are going to talk about gear tooth terminology. Now, if you followed my videos, especially under CAD, when I talked about creating gears, here and there, I talked about different kind of circles that you have in a gear and a few other terms. But here I want to formally introduce these terminologies with the formulas and a few extra things about the teeth of a gear. And here we go with the spur gear, the simplest type of the gear. And then in the next few videos, I also gonna talk about helical gears and then bevel gears and worm gears, the kind of gears that I have not talked about under my playlist machine design. The material here is coming from Shigley, Mechanical Engineering Design, which is, I can say, the best, absolute best book when it comes to machine design. So, first thing first is if you look at the tooth of a gear, what kind of curve are you looking at? So, when you look at this curve here, right, this profile of the tooth, what kind of curve is that? Is that like a circular arc? Is that like an elliptic arc? What kind of curve is that? And the answer is the name of this curve, this profile, is called the involute curve. Now, what is the involute curve? Okay. So involute curve is, first of all, the most common and the preferred profile that is used for the teeth of a gear. What is it? Why is it the most common and the preferred? Let's talk about that. So first of all, the involute of a circle is defined as the curve traced by the end of a string that is under tension when the string is unwound from the circle. You open it up. So let's say here you have this string that is wrapped around the circle, and then you start basically unwrap it or wind it starting from point A naught. Okay, so initially it's at A naught. Okay, then let's say you pin down the point A1. So you put a pin at point A1, and the portion of the string that is between A1 and this point B1 or A naught, between A1 and A naught, you basically make it under tension, right? You apply tension to it, you make it straight and open it up. Then the point A naught goes to point B1. So clearly the length A naught A1 is equal to A1 B1. Okay, this length is the same. That's the same rope. So you just open up that curve and make it straight. So this straight line is clearly perpendicular to the line OA1. It's a tangent line now. Then you move your pinpoint from A1 to A2, and this time all the rope that you had between A0 and A2, okay, all this curve that was between A0 and A2, you open it up, make it tangent to the circle at point A2. Again, this angle is 90 degrees, and the length of it is this time gonna be A2B2. So point basically A naught is gonna now move to B2. It comes to here, and you get this straight line, and you keep basically unwinding more and more of that, and these curves are converted into these tangent lines. And then you trace all of these B points along with the initial A naught, which you might also call B naught. You look at all these B's and trace the tip of this string, and the curve that is created, you call it the involute curve. Okay? So that is the definition of involute, and that's involute of the circle over which you wound you wrapped the string. Now, what's the name of the circle that you started your curve on? It is called the base circle. And the radius of that is RB. Okay, so RB is the radius of the circle. And you can show that if this is the x-axis and this is the y-axis, if you have any point on this curve, if you have any point on this curve, then the equation for that point, the x and y of that point are given by x is going to be rb cosine theta plus theta sine theta, and y is going to be rb sine theta minus theta cosine theta. And theta is the angle of unwrapping basically here. So for instance, if I talk about point B4, right, before the radial line of that is O to A4, the angle it makes with the initial line, which is OA naught, this is your angle theta. Okay, so the angle of unwrapping from initial point, initial radial line to the current radial line is the parameter that you have inside this involute curve, and you can mathematically show that. Now, that's not my goal. I'm not going to prove this formula for you. If you want, you can do some geometry and tricks, and you should be able to find it. So this is the profile of this tooth for most of the gears. Now, why is it the most common, and definitely why is it the most preferred profile? When I say that, you might say, well, is there any other curve that you can use for the profile of a tooth? Because it says the most preferred one, so there should be other ones. Are there? Yes, I'm going to talk about those as well. But first, let's see why this is the one that most of the gears are made of. So why involute curve? The first reason is, which is the most important reason, is involute gears maintain a constant speed ratio regardless of the center distance variation. That is the most important thing. Now, what does that mean? What is the speed ratio? What is the center distance variation? First of all, if you have two gears that are working together, we say the gears are meshed or engaged together. They are working together, right? So typically you call the bigger gear gear, and the smaller gear, you call it the pinion. So if you have two gears like this working together, they are engaged and spinning together, then the speed ratio is typically defined as if one of them is the input and the other one is the output. So let's say, for instance, in this case, this pinion is the input and this big gear is the output. Then the speed ratio is defined as the angular velocity of the input divided by the angular velocity of the output of a system. Okay, so this is what we typically define the speed ratio, input over output, RPM, or and it could be RPM or radians per second. Okay, as long as you stay consistent for both of them. And this speed ratio, you can show that this is equal to the number of basically teeth in the second gear divided by the number of teeth in the first gear. Okay, in other words, if you have a gear with more teeth, it is going to turn slower, and if you have a gear with a smaller number of teeth, it is going to spin faster. So here in this case, this omega of this pinion, which is smaller and it has fewer teeth, is clearly bigger than omega of the big gear, which has basically more teeth, or is bigger. Okay, so this is the speed ratio. Now, this speed ratio, as I'm going to show you, it's also we can show that this is equal to the diameter of basically gear number 2 over diameter of gear number 1. For instance, if this is input over output, that is going to be diameter out over diameter in, or number of teeth out over number of teeth in. Okay, I'm going to show you that in a second. Okay, we're going to see that right down here. But clearly, this depends on the fact that these teeth are well engaged with each other and everything is working perfectly. And one of the conditions for that is this distance from center of gear 1 to center of gear 2, which we call it center distance. This stays constant. In other words, if this one is mounted on one shaft and this one is mounted on another shaft, the distance between these two shafts stays constant. If the distance between these two shafts is variable, because let's say the shafts are flexible, right, and or everything is flexible, but like considerably flexible. And these tip points, or the points that the gears are mounted on, are basically moving a little bit up and down. They have static deflection or dynamic deflection. Then the teeth here are not going to be engaged very well with each other. And that's when you see that instead of this speed ratio be a constant number, it is going to start oscillating and being variable. Now, is that a constant number? Yes, based on what I showed you, it's number of teeth 2 over number of teeth 1. And since n2 and n1 are constant numbers, you expect this speed ratio to be a constant value for 2 specific gears. But again, as long as the distance between the centers is relatively constant, if there is deflection, and let's say this one goes down a little bit, the center, this one maybe goes up, or that one goes down a little bit as well, and this distance changes, then you see that instead of this guy being constant, guess what? This guy starts to be variable. So if C changes, this guy is not going to be constant anymore, and that is not a good thing. Why? Let's say you have a gearbox, and your gearbox has an input of, let's say, for instance, in this case, 2000 RPM, and the output, let's say number of teeth out is twice the number of teeth in. So this one should be like 1000 RPM, okay? So let's say this is coming from the engine. This is getting out of the gearbox. So this is the gearbox transmission of your car, and this one is the one that is going to the tires. And this one is the one that is coming from the engine. So while you keep your foot on the accelerator pedal at a fixed position and you're trying to make the RPM of the engine constant, because this ratio starts to oscillate and not be exactly a constant number like 1 to 2 or 2 to 1 in this case, then you see that this output RPM that goes to the tires is not going to be exactly 1000. So sometimes it goes like 900, sometimes it goes 1100, and so on. So you see, while your foot on the accelerator pedal is at the fixed position, your car speed, which is determined by the spin of the tires, is not going to go constant. Your car at some point goes 40 miles, then goes 60 miles, then goes 50 miles, then go 55 miles, and you cannot keep the car going at a constant speed. So the fact that we need a constant speed ratio is something very fundamental. And in many cases, the shafts that these gears are mounted on, they might have deflections. This distance C, you can never keep it perfectly constant. But involute profile allows you that even if the C changes a little bit, still this guy guarantees that it can keep this speed ratio to a great degree a constant number. That is the most important thing. And here it mentions a reason for it. It says this is due to the common normal at the point of contact always passing through a fixed pitch point. And I can talk a lot about that if you want, but here that's not really my goal. But if you want, basically the common normal is the line that we're going to see. That is this line here that is basically normal to the profile of the teeth, right? So if this is the common tangent, this red line, okay, then this is the common normal. This is the line along which the force is exchanged. And this always passes through a common pitch point, which in this case, that's this guy here. Okay, and it always guarantees that your common normal is passing through that fixed pitch point, okay? The other profiles do not have such a thing, and for that reason, they cannot guarantee a constant speed ratio. So that is the number one and the most important reason. The second one is that making involute gears, manufacturing them, can be done by simple tools. And this is involving some basically involute gear cutters or some gear hobbing machines. And you can see the picture of them here. So this is a gear cutter. This is an involute gear cutter. And you can create basically involute profile, or you can use this hop here, right? This is the gear hop. and these guys can cut basically all sorts of gears for you, not just spur gears. They can cut helical gears, bevel gears, or any other type of gear. And these are very common and not very expensive. With these tools, you should be able to easily cut these profiles and manufacture them very fast and readily. So this is the second reason these guys are very important and very preferred. Okay, now let's answer the next question that was asked, and it was, are there other curves besides involute that you can use for the profile of a tooth? The answer is yes. So involute, we just discussed it. We said what kind of curve it is. The main advantage is keeping constant velocity ratio, easy to manufacture, and there are other things too, okay, like widely used in industry, modular, and so on. Now, what are the other things that are available? The next common profile that you can see and you can hear is called the cycloid, okay? A cycloid curve is mathematically defined as a curve traced by a point on a circle when it's rolling on another circle, where depending on whether the circle is inside the big circle or outside the big circle, you call it epicycloid or basically hypocycloid, right? So if you have a fixed big gear here, big circle here, and you have a smaller circle there, and if you basically put a marker at one specific point on this small circle, when this guy starts to roll on the big one, correct? When this guy starts to roll on this big one, so it comes here, and then it kind of creates this curve, right? Then this kind of curve that it is creating, this is basically called a cycloidal curve, okay? And this one is another one that you can use for the profile of a tooth, okay? Now, what's the advantage of this one? The advantage of this is, since it's basically coming from two basically pulleys, two cylinders rolling on each other, so it's mostly rolling contact. There is minimal sliding between the teeth, and so this has minimal wear in it. So if you have systems that need very small friction in them, like clocks, this is good. And typically in the gears used in the clocks, the profiles I saw are mostly cycloidal as opposed to involute. Okay, so for low load, low friction systems, these are great. But they are sensitive to that center to center distance. They are harder to manufacture, and of course, when it comes to applying load on them, they are not great. So they are not really meant to carry a lot of load, and they are complex to manufacture, sensitive to center distance. But inside the clock, ideally, there is not too much physical load. So if you can just manufacture them, they should actually do a good job without wasting a lot of energy and battery or something. On the other hand, the involutes, although they have this great characteristics, they have some sliding between the teeth. So if you need a system that is low friction, these are not the optimal system, okay? So when friction is critical, these are not the best things. In industrial applications, when the center to center distance can change, and you have big motors to run the shafts with these gears on them, that a little bit friction is fine, and you expect kind of wear and tear, you might use them, although you always lubricate them, so you minimize the wear and tear on the teeth. There are two other ones that are also common, but not as common as the first two. One of them is called conjugate. The other one is called the trachoidal. Okay, so the conjugate one is, they are some kind of custom design curves where the tooth pair maintain a constant speed ratio. So the good thing about them is you can basically optimize some specific motion characteristics, but they need very precise matching. and they are not easily interchangeable, and they are quite a bit more complex than the two other ones to manufacture and to analyze. And so these are kind of newer kind of curves compared to those two. And this trichoidal, this is also a curve. If you trace a point on a rolling circle, okay, it's kind of similar to the cycloidal. This is used in specific devices also, and it's quite a bit compact and efficient. This is good for pumps and rotors, okay, but not really for power transmission systems. So if you have a pump or something, you can use them. You see a bunch of pumps, they have the gears inside them, which creates basically what we call positive displacement, and they compress the fluid. So they are really good for that. And but really, because they have high stress tooth, you really do not want to use them for power transmission. Okay, so these are mostly used for blowers, for as I said, pumps and rotors and stuff like that. So these are not the common thing. The most common one, as I said, for industrial applications, for transferring power, is absolutely still the involute curve, which is easier, cheaper to manufacture, and quite a bit resistance to center distance. So perfectly matches that kind of application. Now that we have seen a little bit about the background, let's talk about more about the terminology. So what kind of terminologies do we have? Now, if you look at a profile of a tooth, there are 4 circles that you can see, or you might even say 5 circles that you can call in it. Not all of them are physical things that you see, some of them are. So if you look at one tooth, there is this flat area on the top, which we might call it topland, or like the crest of a tooth. Then there is this bottom area, right, which you might call it the bottomland, or basically the root, right? So this one you might call crest, this one you might call root, but typically you might call them topland and bottomland of the teeth. And then this top part, this portion here is flat. Then on the side where this involute curve is, you have a face part and a flank part. And this face and flank, they are above and below this imaginary circle, which we call the pit circle. And this is the most important circle in a gear. So what is that? Let's talk about it. But before I move on to that, as I said, there is this topland on each one of the teeth, and from these toplands you can pass this kind of physical, visible circle, you might call, which is called the addendum circle. So addendum is the maximum diameter that is possible in a gear passing through the top of the teeth. On the other hand, there is this circle that is passing through the roots or the bottomland of these teeth, and that is called the dedendum circle. So addendum and the dedendum, these are the max and min diameters that are physical, and you can potentially basically see portions of them. Now, somewhere between this addendum and dedendum circle, as I said, there is this imaginary circle which is called the pit circle. The part on the side of the part on the involute curve that is above the pitch, you might call it the face. The one below it, you might call it the flank. So let's talk a little bit about this pit circle. What is this imaginary circle? Why is it very important? The reason is this. If you look at 2 gears that are meshed together and they are working together, and you show the addendum, dedendum, and the pit circles of both of these gears, what would you see? So here they are shown. You can see that when these 2 gears are meshed, the addendum circle of this one is now somewhere close to the dedendum of the other one, but it will never touch that. Okay, it only when these 2 gears are touching each other and they moving with each other, this distance between the addendum of one and dedendum of the other one keeps changing, sometimes it reaches some very minimum below which it never goes, and that one is what we call the clearance circle. So clearance is basically the maximum depth that the tooth of the matching or basically engage gear with this one, it comes inside and will never pass that small gap. And that small gap itself, we just call it clearance. Okay, so there will be always a gap between them, and it should be, otherwise they will hit each other and they will be jamming. Good. Now, if you look at the pitch circle of this gear, and if you look at the pitch circle of the other gear, what would you see? Yeah, you see the important thing is the pitch circles of these two gears are tangent to each other, as you can see. And that is very important. The pitch circles of two meshed gears are tangent to each other, and their diameter is shown by D, or D sub P. And what's the importance of it? The importance is if I replace these two gears and replace them by two simple, basically drums, or two simple cylinders that are spinning each other just because of friction between these surfaces. Okay, so there is friction between the material, and when one spins, it spins the other one, right? So if you replace each one of them with an equivalent drum or a pulley, what would be the diameter of each one of these pulleys? The answer is that pitch diameter. So this is like D1, this is like D2. So these are the equivalent diameter for these gears, equivalent in terms of what? In terms of the speed ratio. So if I want to find the speed ratio between these two teeth, between these two gears, that speed ratio, I can show you that also the speed ratio, which is omega 1 over omega 2, can be defined as D2 over D1. Okay? Because we know that if these are just two drums, or you might call them belt and pulley, right? So if there is a belt going around them like this, you know that the speed ratio between these two drums or these two pulleys come from this formula. Okay, we know that from kinematics of rigid bodies. So that's the exact same thing is now applied to these gears, because these two circles are tangent to each other. Okay, so that is the pitch circle, and that is the diameter of the pitch circle. That is the imaginary circle. So far we have seen 3 or 4 circles, I would say. There is the addendum and dedendum circles. These circles are the one that you can physically see. Then we have, of course, the clearance circle. This is the circle that is the gap between addendum of one and dedendum of the meshing one. And then there is the imaginary one tangent from the two, that is called the pitch circle. Okay? And below the pitch circle, there is another circle. Below the pitch circle, there is another circle. This circle is called the base circle. And base circle basically has the same meaning that we had for the involute curve. So if you look at them here, you can see it, right? Look here. Let me show you. So this is the addendum of it, this is the pitch of it, and guess what? This is the base of it. Okay, and this is the dedendum. Yes? And then you might say that, well, look at where the base circle is on this gear. Look how close it is to the dedendum. Would you say that that could be the same circle as this clearance circle? Because the clearance circle is also very close to the dedendum. Is that the case? The answer is not really. Although clearance circle and base circle are very close to each other, they are not exactly the same thing, okay? So this base circle that I did for you, maybe it's actually a little bit even closer to the clearance. So maybe it's here. So what's the difference between these? As I said, base circle is where your involute curve starts. So above this base circle, okay, this is your base circle. Above the base circle, your profile is involute. So this portion of the profile, this portion is involute. You might say, what about this portion here below it? This portion here. What is that? The answer is this is not involute. If it's not involute, what is it? Well, it could be anything. It could be a straight line, it could be curve, it could be anything. Why doesn't it matter? Why could it be anything? The reason is when these two gears come into contact with each other, right? As I said, this contact point, when the teeth, let's say they are spinning like this. When the teeth on the right side starts engaging and on the left side they release the engage, the contact point on the teeth starts moving, right? So initially the contact point is here, then it kind of moves a little bit, but as this contact point is moving on this profile, it is going up and down on this profile, the maximum point that the contact point, so let's say this is your contact point here, the maximum point that this contact point goes down is at most up to the base circle. It never goes below the base circle, okay? The contact point. The contact point that is on the profile of the tooth, this guy will never typically goes below the base circle. You might say, what about the clearance? The clearance is only for the tip, okay? So only the tip, only the addendum, right, can come down to the clearance. So for instance, if I draw this here for you under the worst case scenario condition, here the addendum of the matching gear is touching the clearance, but the contact point, which is here, it doesn't go all the way to clearance. It only goes at most to the base circle. Okay, so do you see the difference? One of them is for the tip point, one of them is for the contact. The contact will never come all the way to the tip. It only oscillates in some range of the face or the flank. It never goes all the way to the tip, never goes all the way to the bottom. It only goes up to so much and it only goes down to so much. The bottom portion of it is the base circle. Okay, so there are 5 circles that you can define for a gear: addendum and dedendum physical, base circle, clearance circle, and pit circle are not physical. I mean, they're imaginary. Yes, you can draw them, you can measure them, there are formulas for them, but not something that you can exactly draw with a marker or something on a gear. Okay, so if we go back here now, if we show the diameter of the pit circle with D, or dp, diameter of the base circle is related to diameter of the pit circle by this formula. Diameter of base is diameter of pitch times cosine of an angle phi. What is this phi? It is called the pressure angle of the gear, and this is another one of the very, very important terminologies and parameters in a gear. It's called the pressure angle. So what is the pressure angle? The pressure angle is the angle between the line of action and the common tangent to the pitch circles of the two gears. Well, what does that mean? Let's go back to this diagram and again take a look so I can define for you the pressure angle, which, as I said, is one of the important parameters in a gear. So look here. Here I have, again, 2 gears that are meshed. And if you look, this is the line that is connecting center to center, this line. These are the two pitch circles. And since these are the two pitch circles, I can draw a line that is tangent to both of these pitch circles. That is this line here in green. This line in green is the common tangent to both of the pitch circles. On the other hand, when you look at the profiles, if you look at these profiles that are touching each other, this profile and this profile, they are also curved. So there is a common tangent to them and there is a common normal to them. This line here is the common normal. This line is what we call the line of action. This is the line along which the normal force between the teeth are exchanged. Okay, so this one, this line here, this is called the line of action, the common normal, the line of exchange of force between the teeth. So the angle between this line of action and this common tangent, this angle here, this angle is what we call the pressure angle. Okay, and this angle plays a very important role in the gear, as I'm going to explain to you. But the first thing of it is you can show that the diameter of the base circle and diameter of the pitch circle, or the radii, their corresponding radii, are related by cosine of phi, and it's not really super hard to show here. Okay, it's not really that super hard to show. You can show that basically you can form a triangle between two radial lines, one with RB, one with R, and the angle between them is phi, and R and RB are basically related to cosine of. And that is a triangle like this, basically, if you want it. Let me see if I can draw it for you. So that is something like this. Look. And then we have this. And then we have this. This angle is 90 degrees. You can show this is R of B, this is R, and this angle you can show this is phi, and RB and R are related by cosine of phi. Okay, it's not really such a hard thing to show. Again, I'm not after proof here, but if you want, I can show them to you in a future video, or you can look it up yourself. So these two are clearly related. Now, I said this is an important parameter. Why is it an important parameter? And can I have any number for it in a gear? So can I have a gear with a pressure angle of 10 degrees? Can I have one with 40 degrees? Can I have one with 35 degrees? Can I have any pressure angle that I want? No. Typically, there are only a few options for pressure angles in the gears. The most common ones that you can see are 14.5 degrees, 20 degrees, and 25 degrees, okay? 14.5 degree at the moment is kind of mostly obsolete. Most of the gears are not using 14.5 degrees anymore. The one that is very common these days is the 20 degree pressure angle. Now, in high strength, compact gears, in the gears that carry a lot of load, you can use a 25 degree as well. But typically, as I said, 14.5 is mostly obsolete. You still see that when you go to CAD software and you want to create a gear. If you are doing it parametric using the toolbox or something, it allows you to pick a 14.5. But again, mostly it's 20 degrees. That is common. So why is this angle any important? So let me show you with an example with what happens. So if you pick a low pressure angle or a higher pressure angle, what is the difference? The first one is, if you pick a lower pressure angle, your tooth shape is going to be thinner. Here is going to be thicker. So here you might have something like this. Here you might have something like this. Clearly, this one can carry more load than this one does. So this is stronger, this is weaker. Now, this has some good thing about it. Because of these big slopes, it has less friction when these gears contact points are touching each other and they slide. So the friction here is less than this one is. But for many industrial applications, we can compensate that friction by big motors and good lubrication. We really care to carry more load, so we want basically thicker profiles as opposed to thinner profiles. Okay, so and bigger pressure angle are allowing for such a thing. So they have bigger load capacity, they have lower. What about the bearing load on them? Now, clearly, because the transmission load is bigger on them, also the radial load is bigger on them. So they clearly need better bearings. Okay. The other thing is backlash sensitivity. We're going to talk about what backlash is. These guys are sensitive to backlash. These guys are less sensitive. That is another good thing for them, that these guys are less sensitive to backlash. These guys are more sensitive. So this is a good point. And also, as I said, this is a good point, but they have other things, right? So these are weaker. They cannot carry much load. And about the alignment sensitivity, these guys can easily jam and they are higher sensitive to alignment. These are lower sensitive. And alignment here is basically that two axes are like parallel, the distance between them stays constant, and so on. So center to center distance, these bigger pressure angles are less sensitive. So in general, mostly today's we are using bigger pressure angles, although you still can generate these, but these are more kind of obsolete. And you might say, where does that come from? Well, if you look here, when this angle becomes bigger, when phi gets bigger, cosine of phi drops. And when cosine of phi drops for the same diameter of pit circle, diameter of the base circle goes down. So when phi goes up, cosine of phi goes down. Therefore, if d is constant, d base is going to go down. So basically, instead of the base circle being here, you are shifting it a little bit further inside, so this gear can go further down and it is going to get thicker, okay, because you are shrinking the base circle. So this is the pressure angle. I also talked about the addendum circle and the dedendum circle. Let me show you a couple of other things before we go to the gear modulus. So what else do you have on a gear? So one of the things that I need to mention is, of course, we have the face width, which is a very important thing, right? So that is this thickness of the tooth, and that is very important in how much stress it can tolerate. So that is one of the factors that you can pick in a design if possible. Another thing that you can control the amount of stress in the part is this fillet radius. So the bottom portion of the teeth, when this curve meets the circle, if you don't fillet it, you have a sharp edge and you can have a stress concentration. So to reduce the stress concentration and increase the life of the teeth, what you need is to fillet all of these internal edges. And so depending on that fillet radius, you have different concentration factor coefficients. So these two parameters will affect the life of the gears as well as, of course, the pressure angle. Okay, so you can see that as well. Now let's talk about the gear modulus. One of the most important parameters, probably the most important parameter in a gear, in addition to the number of teeth, is gear modulus. Gear modulus or module is defined as the diameter of the pit circle divided by the number of teeth. Is called the gear modulus. it is the customary unit of length used in millimeter. It is the index of tool size in SI. Tooth size, sorry, in SI. So basically, when you want to pick a gear, if you want to pick a gear, you have to provide two pieces of information at bare minimum. The first one is the number of teeth. You have to say, hey, I want a gear with 48 teeth. The second one that you need to provide is the gear modulus. So I want the gear modulus with 4 mil, okay, 4 mil per teeth. So if you have the gear modulus and if you have the number of teeth, guess from these two, the first thing you can do is diameter of the pitch circle is determined. That is n times m. Okay? So diameter of the pitch circle is n times m. And so these two are the first two important parameters that you need in a gear. The third parameter that is important was that pressure angle, phi, from which you can determine the diameter of the base circle from this formula that I just showed you. Let me see where I left it. There we go, here. Okay, so three important parameters so far: n, m, and phi. Now, what's so important about this gear modulus? Why is it so important? Why couldn't I not give you the diameter of the pitch circle directly and you have to find it through this formula? The reason is this: if I want to engage two gears together, something of these two gears have to be the same. Guess what? They're moduli. The modulus of gear 1 and modulus of gear 2 should be equal, otherwise you cannot mesh the gears. Because this one tells me the space that I have per number of teeth, or the size of the gear per number of teeth. So if M1 equals to M2, that means D1 over N1 equals D2 over N2. What does this mean? It means that if one gear is bigger, the number of teeth on it should also be more, so this ratio is the same as the other one. So if you have one gear that has, I don't know, 24 teeth and the other one has 48, then diameter of this guy should be twice as big as this diameter, because the ratio of the teeth is 2 to 1, so they can work together. Otherwise, when this top gear is, let's say, bringing one tooth to get engaged, the bottom gear does not have a corresponding tooth to get engaged, or it might have more than one ready in line to be engaged. So to have a proper number of teeth, you also need to have a proper diameter, and that is the exact ratio as the number of teeth, okay, which you can see here, right? Another way to say this is you can also say that D2 over D1 is the same ratio as N2 over N1. So this is extremely important. That's why we identify a gear with a modulus. So if I want to mesh two gears, let's say I say the first gear is 24 and a gear modulus of 4 millimeters per teeth or per tooth, right? What can I pick for the second gear? Clearly the second gear should have the same modulus. It should have a 4, but the number of teeth of that is what? That is up to you. For instance, I say I want 48. Why? Because I want the speed ratio of 2 to 1 or 1 to 2. Well, when you give these two pieces of information to that person, he or she knows that the second gear you want should be twice as big as the first one is. And that is the information that we are passing. And since the speed ratio is N2 over N1, based on what we just learned, you can say that is equal to D2 over D1. Now, I know I just had a typo. I just fixed it. I had D1 over D2. I just fixed it. It's D2 over D1. So the speed ratio of two gears is either N2 over N1 or D2 over D1, which is omega 1 over omega 2. So this is the formula for speed ratio. Okay, good. What else do we have? The next few things that we need to add is the diametral pitch. Diametral pitch is kind of the same thing as gear modulus, but this is for the US system as opposed to SI system. In US system, when you want to identify a gear, instead of giving the modulus of the gear, you give the reciprocal of that, which is N over D. So instead of D over N, you give P, which is N over D, and you call that diametral pitch. It's the number of teeth per pitch circle diameter, so you can say this guy is the same as 1 over M. Okay, so in US system, we give a diametral pitch. For instance, we say 2 teeth, right, per 1 mil instead of 4 mil per 1 teeth. Okay, so these are reciprocal of each other. So if you hear one or the other one, they are basically the same thing. Now, one thing that you might say is, okay, you gave me a formula for the diameter of the pitch circle. You said that the diameter of the pitch circle is this one here, right? D equals N times M. Also, I have a formula for diameter of the base circle, D times cosine of phi. What about this addendum and the dedendum circle? Do I have a formula for their diameters? And the answer is yes. How? So here we define two parameters, addendum and dedendum. Addendum is the distance, radial distance between addendum circle and the pitch circle. The other one is the distance between pitch circle and the dedendum circle. These two values, addendum and dedendum, you can show that for a gear in the SI system, the diameter of the addendum is given as the diameter of the pitch circle plus 2m. This 2m is your addendum itself. And diameter of addendum is d plus 2m. On the other hand, diameter of dedendum circle is d minus 2.5m. So 2.5m is the dedendum. Okay, so here you have the formulas for the diameter of those two circles. Okay, only a few parameters left and we should be done. The next thing you have is called the circular pitch. This distance here, circular pitch. What is this? It's pitch, you know, for a thread. If you remember threads, for a thread, pitch was the distance between one thread to the next, correct? Two similar points. For a gear, you can define something similar. Pitch is defined as the distance between two similar points on the profiles of two adjacent teeth. Now, this distance, the length of this arc, it depends on which 2 points are we talking about. Are you talking about these points on the addendum circle similar, these 2 points on the dedendum circle similar, or where? And we typically define these 2 points to be on the pitch circle. So this distance, we call it circular pitch because first of all, it is on the pitch circle. It is a distance between 2 corresponding points and it is an arc. So we call it circular pitch and it's the distance between 2 similar points. What's the formula for it? It is very simple. It is the whole diameter, whole circumference of the pitch circle, pi times d, divided by the number of teeth. So pi d over n, and since d over n is m, you can write it as basically pi times m, or you can write it as pi over capital P, where capital P is this diametral pitch. Okay, so circular pitch, small p is pi times gear modulus. Now, it has 2 parts. One part of it is tooth thickness. The other one is the space between the teeth. Let me show you that one as well. So when you look at this arc, you see that this arc can be broken down into two parts. The first part is between these 2 points on the profile of the tooth, this portion. The other portion of it is this gap between them. So this gap is called the space, and this thickness on the tooth is called the tooth thickness. So circular pitch is equal to the thickness plus the space. Okay? Now, one question. Are each one of these half of the circular pitch, or they are not equal? Is the thickness and the space the same? The answer is no. The space is a little bit bigger than the thickness, because when the other one is coming in and getting engaged with that, remember the two circular pitches are tangent, then clearly you want that thickness that is coming in to be able to fit inside this space. So the thickness should be a little bit less than space, otherwise the two teeth will jam and they will not be able to engage. And this difference between the space and the tooth thickness, this difference between them is called backlash. So backlash is the gap that you will get when one tooth is engaged with another one. The gap, if it touches one, the gap it has with the other one, and you can define it over this pitch circle. This gap is defined as backlash, and it should exist, otherwise you cannot get them engaged. Now, you know this backlash is not a very great thing. Why? Because when the teeth gets pushed by this one and it is coming to this one to get engaged, it is going to hit it. So right there, you're going to have an impact. And because of that impact, there will be stress between the teeth, and the life of the tooth goes down. So it is going to weaken over time the teeth, plus when it has impact and it hits, it's going to be bouncing back a little bit. So that will change the angle of these teeth. And if their angles are very important, they cannot tolerate some small oscillation, right? Because when it hits, it's going to bounce back. So you might have a little bit oscillation in the rotation. If that thing is very important and the angular position of these gears are very important, then you have to minimize backlash as much as possible. But remember that backlash is very critical. Why? Because backlash allows for these teeth to get engaged to each other without any jamming. And if this backlash is very, very small, you might say, what's wrong with making it very small? The problem is when the gears start to heat up, when there is a lot of power exchange between them, and even with lubrication, the system starts to heat up, these gears start to basically get bigger, right? So they're going to enlarge, they're going to get bigger, expand, and when they expand, then this gap will be filled, and that is when you see the gear system start to jam. So you need some bare minimum backlash to avoid the thermal expansion, jamming of the system, and to minimize that, you always need to lubricate the system and make it cool down and not thermally expand so much. Okay, so backlash is very critical. And clearance, we define it, clearance is the radial distance between addendum of one and dedendum of the other one. This is the radial gap that you have between the teeth. The tangential gap that you have between the teeth is called backlash. So hopefully now you can see the difference between backlash and clearance, because these two are very, very important when it comes to meshing gears. So hopefully this long video was useful to you. You learned a bunch of things about gear tooth terminology, and stay tuned for a few more upcoming videos. Thank you.